50 years ago in Scotland, one man had a brilliant idea. An idea that today pits science detectives in Europe and America against each other in a $10 billion race to solve the riddle of what you, me, and everything around us is really made of. It's a journey into the heart of matter, plunging into the core of our physical being and of the physical world itself. But will this journey into the subatomic universe revolutionize our understanding of nature? Or will it reveal just how little we really know about who we are and what we're made of? Space, time, life itself. The secrets of the cosmos lie through the wormhole. What are we really made of? You, me, everything around us. That simple question has kept people guessing for thousands of years. In ancient times, the answer was easy. Everything in creation was made from one or more of the four elements: earth, air, fire, and water. When I was a kid, in not quite so ancient times, we were told that everything is made out of atoms. But in the last few decades, scientists have looked inside the atom and found that things are a lot more complicated. Despite all of our knowledge, we still don't understand the true nature of matter. But right now, thousands of investigators are following hunches, tracking down suspects, and getting closer than ever to learning how we and everything around us fits together. And they're doing it by breaking things apart. When I was 6 years old, my father gave me his old pocket watch, a timekeeper. How does this work, I wondered. I decided to find out. Taking it apart was a lot easier than putting it back together. But I learned a little about what makes things tick. And that's pretty much what particle physicists do today. They smash things up and look at the debris through extremely powerful microscopes.
We do what kids do. We smash things, and we look to see what comes out. And so to do that, we need to smash things harder and harder and harder to see what's smaller and smaller and smaller.
At Chicago's Argonne National Laboratory, Bob Stanek builds machines that peer into the subatomic world.
So this is our advanced photon source, a microscope that's about a half a mile around, and it contains 33 stations where 33 individual experiments can go on, measuring tiny structures of whatever these guys feel happy measuring. If you remember way back in high school, when you looked through the microscope and you said, wow, look at all that stuff, how neat it is. It's amazing that ordinary light and optics can bring you to such a detail level. However, for a lot of things nowadays, you need more than just that ordinary light. You need to get smaller and smaller and smaller. With the APS, we can see things much smaller than we could see with our standard microscope. We could see things a factor of 10 smaller, a factor of 1,000 smaller, a factor of 10,000 smaller. In fact, we can see things that are 10 to the 10th smaller than what we could see with ordinary light. We can see molecules, we can see viruses, we can almost see the structures of life.
The ability to take pictures of molecules and atoms is an incredible thing, because only 100 years ago, the atom was just a theory. At the dawn of the 20th century, it was believed that if atoms existed at all, they were either empty shells or solid little balls. Then one investigation changed everything. It was the brainchild of Ernest Rutherford, the Sherlock Holmes of particle physics. Steve Naun is a professor at MIT and a team leader on the world's biggest particle accelerator, the Large Hadron Collider in Europe. Steve is going to reproduce one of the most important experiments in the history of science, Rutherford's probe into the structure of the atom.
This experiment is the same as Rutherford's experiment. We use the same kind of gold foils and send millions of particles through these gold foils. Rutherford thought that all the particles would essentially go straight through and not deflect at all, but that's not what happened.
The Rutherford experiment is like firing bullets at a haystack. The particles are like bullets, and the atoms in the gold foil are like haystacks. If the haystack is empty, the bullets go straight through. If the haystack is packed with cannonballs, all the bullets bounce back. If there are a few cannonballs in the center, some of the bullets will bounce back. And that's what happened. When Rutherford fired his particles, most went straight through, but some sharply bounced back from the center of the target, upending the conceived wisdom of the time. Something small and hard was down in there, deep inside the shell of the atom.
This is the evidence for a very heavy, very small object at the core of the atom, the high-density nucleus surrounded by a vastness of empty space.
In fact, the nucleus of an atom is 100,000 times smaller than its radius. It's equivalent to the head of a pin in the middle of a football stadium. After Rutherford, physicists probed further into the atom. They found that it is built out of three parts: the protons and neutrons that form the nucleus, and the electrons that form the shell around it. Between them, they make up atoms. Atoms stick together and form molecules. Out of the molecules, we get more complex shapes, from a strand of DNA up to the 7,000 trillion atoms that form a human body. For a time, the atomic theory of the universe seemed to explain most everything. But then physicists started breaking atoms apart, and they discovered a slew of mysterious new particles that turned their theories upside down. The most frightening was called antimatter, matter's evil twin. If just this much touches ordinary matter, it will level a city. So why are scientists trying so hard to make it? Turns out it may hold the secret to the mystery of matter. When scientists first smashed atoms apart, they uncovered their essential building blocks: protons, neutrons, and electrons. Next, they built machines that let them smash these tiny pieces together, and out came strange new particles. Perhaps the strangest is the stuff we call antimatter, matter's polar opposite. It's the most explosive substance in the universe. When matter and antimatter touch, they violently cancel each other out. Physicists say they annihilate each other. It triggers an enormous explosion. How big of an explosion? Less than half a gram of antimatter rice would produce a 13-kiloton blast, as big as the Hiroshima bomb. Professor Frank Close is a theoretical physicist at Oxford University.
Antimatter is a perfect opposite to matter. If I was made of antimatter, I would look exactly the same as I do today. If you looked at the atoms that I'm made of, they would look exactly the same if I was made of anti-atoms. It's only when you get inside the atoms that you see the difference. That the atoms that we're made of have little negatively charged electrons whirling around a big, bulky, positive nucleus.
And the anti-atoms? Ask this man, Joel Fagans, an antimatter investigator at the University of California, Berkeley.
Antimatter is everywhere in the universe. For instance, this banana contains potassium-40, an isotope of potassium which emits positrons. Positrons and other forms of antimatter are difficult to study, however, and that's my job. That's what I do, is to study antimatter. I was partially inspired to do this by this experiment over here, the Bevatron accelerator at the Lawrence Berkeley National Laboratory. The Bevatron was the first giant particle accelerator. It's being torn apart now, but back in the 50s, it was the center of the world for physics research. The same techniques that were used in the Bevatron to accelerate particles are now used in the enormous particle accelerators that are throughout the world.
Particle accelerators are like giant microscopes that let us peer into the subatomic world. They break matter down into its smallest components. Drilling down far enough to detect antimatter requires taking protons from an atom's nucleus, trapping them in a vacuum, then shooting them into a ring of giant electromagnets.
So a particle accelerator works by starting protons going around in a circle, in a ring. And every time they go around, you give them a little kick with an electric field, so they get going faster and faster and faster and faster and faster until they're almost at the speed of light. Well, they're going almost the speed of light in a real particle collider. But here, they're not going that fast. Yet.
So, protons in this direction interact with protons in this direction, and at some point they come like a car crashing together. And you can imagine what happens when a car crashes together. Pieces fly all over. And around that interaction point where the cars crash together is where we have our detector. So, and this happens millions and millions and millions of times every second.
When you break protons apart, you release incredible amounts of energy. Strange things come out of the explosions, including tiny particles that flare into existence and disappear in billionths of a second. Particles like the antineutron and the antimatter version of the proton. Theorists had predicted they existed in the 1920s. Decades later, the Bevatron proved they were right. Suddenly, the world we thought we knew got a whole lot stranger.
Positrons from things like radioactive decays, like in the banana, or from cosmic rays, form one half of an antimatter universe. Antiprotons from machines like this, and from cosmic rays and other natural sources, form another half of an antimatter universe. Put them together and you've got a complete antimatter mirror universe, which just looks like ours, except everything is backwards, everything is mirrored together. And that's a little bit surprising, shocking maybe, because matter universes and antimatter universes aren't very compatible with each other, because when you put them together, when they touch, they annihilate or blow up. So how did we come to be here? Because if there was just as much matter as antimatter in the universe, it should have all combined together and left us with absolutely nothing.
The tiny bursts of light you see here are antimatter electrons, or positrons. When they leak out of this small radioactive disk, they hit the oppositely charged electrons of the normal matter in the chamber and instantly annihilate, creating these flashes of energy. Positrons and electrons are the smallest particles imaginable, so the fact that you can see them explode with the naked eye gives you a hint of how much energy is being released. Antimatter is the ultimate high explosive. Some worry that in the wrong hands, it could be used to create an antimatter bomb, the ultimate superweapon.
There's no way we're going to destroy the Earth using antimatter here. It's absolutely impossible to get a large amount of antimatter around simply on the basis of economics. If you wanted to make even a couple of grams of antimatter, you'd have to run this facility for, in fact, thousands, if not tens of thousands of years to make even a few grams of antimatter. And this is a fundamental physics issue. This isn't an efficiency issue. It's not as if we're going to get much better at this than we currently are at it.
So you can relax. The world is safe. Antimatter is what we are not made of. But the fact that it exists at all reveals how alien the universe really is, and how little we understand the cosmic forces at work in the heavens and deep inside our own bodies. The discovery of antimatter was followed by deeper probing into the heart of the atom on larger, more powerful particle accelerators. But physicists didn't like what they saw. The closer they looked, the less things made sense. The accelerators exposed a bewildering array of mysterious particles, dozens of strange pieces of matter, all seemingly different. Some were incredibly heavy. Some had no weight at all. The subatomic world earned the nickname the Particle Zoo.
When we were learning about the zoo of particles that were not defined, it was pretty chaotic, and it just didn't look right. And you're thinking, this is bullcrap. There's got to be something better than this, because this is just all, like just categorizing stuff, black magic, and people just didn't know what they were doing.
Physics is a quest for simplicity. This was chaos. Why? To help crack this mystery in the 1970s, the United States built Fermilab, a high-energy research facility 30 miles outside of Chicago. Fermilab sits on top of the Tevatron, a 4-mile-long particle accelerator. Nobel Prize-winning experimental physicist Leon Lederman conducted many of his experiments here. But for decades, he groped in the dark like everyone else, trying to make sense of the messiness of the quantum world.
Little by little, more and more particles got fed into the hopper till there were a couple of hundred particles, as you know, in 1950s, 60s, and 70s. And then people started organizing these particles into family groups. And out of this, late 70s, early 80s, came the organization called the Standard Model. But it was a gradual process. And it's like a jigsaw puzzle. You got the right piece and everything fell together, and there was the painting on the box cover.
After studying thousands of these jigsaw puzzles, physicists began to understand what they were looking at. Rob Rosa runs the giant detector that takes pictures of matter and antimatter collisions inside the Tevatron.
Behind me is an event display of a proton-antiproton collision occurring inside the CDF detector. You can imagine the proton coming from one direction in and out of the screen and colliding at the center point. And so by looking at the bend or curvature of the particle, if it's curved in one direction, that particle is positively charged. If it's bent in an opposite direction, that particle is negatively charged. So if we just break this event down, you can see a single long pink object pointing to a big pink cluster. The more the color, the more energy that particle had. So you can see here's a single particle that gave up a bunch of energy right in the initial part of the calorimeter. That's indicative of an electron. Over here, you see a single line that's giving up energy in the back half of the detector, more characteristic of what a muon object would look like, a muon being a heavy electron. So we can start to get a lot of information by just looking at a couple of very simplistic ideas in terms of where the particles traveled, how much they curved, and where they deposited energy in the detector.
Today, after years of reading these subatomic tea leaves, physicists feel they are getting closer to answering the question, what are we really made of?
The stuff that we are made of today only requires maybe a handful of little particles. The atoms on the outside are electrons whirling around, like planets, if you like. There's a nucleus in the middle of the atom, which we used to believe was made of protons and neutrons. Well, it is, but deeper down, they in turn, like going to the heart of the cosmic onion, are made of little things called quarks. And two types of quark, an up quark and a down quark. And that's it. An up and a down quark, joined together in different ways, ultimately make the atomic nucleus. An electron whirling around the outside make the atom. Throw in a neutrino, which is created in radioactive processes, and that's the basic particles that make up everything that you see around you. There's also the photon of light, which we are seeing with right now, and that pretty well is it.
Most of the atoms in our body are made of nuclei and electrons, and the nuclei themselves are made of protons and neutrons, and the protons and neutrons are made of quarks. And, of course, you say, what are the quarks made of? And that's where we're stuck. For the last 40, 50 years, we've been studying the quarks, try to find something inside, and we get the same results we had for the electron. There's nothing inside. The quarks don't have any size. The radius of the quark is 0. It's a little bit like Alice in Wonderland. Remember when Alice saw the Cheshire Cat sitting on the branch of a tree with a big smile? And much to Alice's great astonishment, right in front of her eyes, the Cheshire Cat started to disappear. And finally, poof, it was gone. But it left behind one component, its smile.
That quark smile is a tiny box stuffed full of energy. All matter is actually made of energy that has congealed into particulate form. So that appears to be what we are made of, at least as far as we can see right now. But knowing this opens up an even greater mystery, which is, why does the stuff we are made of behave the way it does? Our explorations of matter reveal that everything is nearly hollow. You, me, and everything in the universe. It's all empty space with a few pinpricks of matter floating in a void like rocks adrift in the vastness of space. But how do these pinpricks of matter form into shapes and structures? There must be something holding it together, some sort of glue in the ocean of emptiness. The question is, what? Today, we think we know what we're made out of, the incredibly small building blocks that form all the matter in the universe. But finding these bits and pieces of matter revealed another, even more challenging mystery. Why are things solid? Why do they have mass?
Matter is mostly empty space. Every now and then, you find the point of an atom, but most of the time, it's empty space. So that point of atom and that point of atom and so on, how are they held together? How are you held together? How am I held together? It's not glue. You know it's not glue. It has to be some exchange of fundamental properties. That exchange of forces has to happen, even though you don't see it, has to happen at the global level everywhere.
Empty space isn't empty at all. It's filled with forces. When these men toss this basketball back and forth, they're transferring the momentum of the ball from one to the other, which pushes them apart. A complex exchange of invisible forces talking to each other.
So there are four fundamental forces: the gravitational force that everybody knows about, the electromagnetic force, which mostly everybody knows about, the weak force, which you don't know about, and the strong force, which you don't know about. The weak force is what determines radioactive decay, how uranium decays into whatever it decays into. That's governed by the weak forces. The strong forces are what holds the proton together, what holds the quarks into three pieces that form a proton. So us guys are doing the weak forces and the strong forces. And what we don't understand is the gravitational force, and we think we understand the electromagnetic force.
Just as we can't see the things we're made of, we can't see the fundamental forces around us, but we know they're there. Finding out how these forces work and where they came from in the first place is the great quest of modern physics. Solving this mystery could reveal the universe's most closely held secrets, not just what we're made of, but why the stuff inside us holds its shape. The key breakthrough in particle physics was the discovery that certain particles are actually force carriers. For instance, photons, particles of light, carry the electromagnetic force. All the forces have these carriers. We haven't found them all yet, but we've found enough to know they're there. And we know enough about how they interact to realize that at extremely high temperatures, around 1,000,000 billion degrees, the electromagnetic and the weak force begin to merge. This merging is called electroweak unification. You don't have to understand it. I certainly don't. But to physicists, it was like finding the missing link. It led the way to one of the most successful theories in the history of science, the Standard Model of particle physics. It's been proven correct again and again over the last 40 years. But there is a problem with the Standard Model, a big problem. And it goes back to the particle zoo, strange particles that turn up when you smash together protons to see what's inside. Subatomic particles have a huge range of weight, or mass. For instance, one point-like quark can weigh 200 times more than the point-like electron. And these particles have even heavier cousins weighing 100,000 times more. The Standard Model cannot explain why there is such a wild range of masses, or even why particles have any mass at all. Fixing this problem became the next great quest of modern physics. Salvation came in the unlikely form of this man. Meet Peter Higgs, an unassuming professor who set off one of the largest and most expensive investigations in the history of science. There was a gaping hole in the Standard Model of the universe. Peter Higgs put a plug in it. Higgs theorized that a vast field stretching to infinity runs through everything. When certain kinds of particles interact with the field, that interaction is what gives those particles mass. If Higgs' theory becomes fact, we may finally understand why things are solid. But at first, Higgs had trouble getting his theory accepted. A paper outlining the idea was rejected by CERN.
I was indignant because I thought what I'd done had possibly important consequences. So I rewrote the paper by adding on some extra paragraphs. And instead of sending it back to Geneva, where I thought the people at CERN didn't understand what I was talking about, I sent it across the Atlantic to Physical Review Letters, the corresponding American journal, and it was accepted.
The paragraphs Higgs added predicted that the mass-giving field would have a matching particle, a force carrier called the Higgs boson. And this matching particle could theoretically be created in a particle accelerator. Gradually, experimental physicists became excited by Higgs' idea.
What happens with the theory is, of course, a small number of theorists push this idea, they love it, and little by little, more and more theorists climb on board. You know, it's like the train, woo, woo, we're taking off from the station.
In one of the great ironies of modern science, CERN, the organization that rejected Higgs' paper, has just spent $10 billion building a machine to find the Higgs particle. But what exactly is the Higgs? Ask a half dozen physicists and you'll get a half dozen different answers.
The Higgs. It's a tricky thing. We come up with an analogy for the Higgs boson.
There's the analogy with something being dragged through treacle, but for me that's misleading because this is a dissipation of energy, and it isn't like that.
That's a pretty bad analogy for the Higgs.
What I've read on the Higgs is, in my mind, very confusing. Here's the way I understand it. A bunch of reporters standing in a room, crowded room. And so me and President Obama want to make it from the entrance of this room to the exit of this room. So we go in, and what happens? Of course, all the reporters glom on Mr. Obama. And Obama over here, he just makes a beeline right to the exit door. So basically, with no inertia, I can make it to that door. Whereas Mr. Obama has a lot of inertia, a lot of mass. So this Higgs field affects one particle more so than another particle.
You must be able to come up with a more...
Well, when we see what they look like, we'll come up with a better analogy. Right?
Another analogy, yeah. Something involving cars or something. No, I don't know.
However you describe it, the Higgs solves a slew of problems, starting with the particle zoo.
It's a very elegant idea because if you accept it, then our whole picture of particles becomes simpler. There are not so many particles. It's the mass that makes it look as if there are many particles. A little bit like a kaleidoscope where you look in with a lot of mirrors and there's only one little pattern, but it's reflected and reflected in mirrors and it looks very complicated. The Higgs phenomenon is a very satisfying way of simplifying our standard model.
The Higgs gives mass to the basic seeds of matter, such as the electron in atoms and the quarks inside protons. Because the mass of the electron helps determine the size of the atom, the Higgs gives structure and form to everything we know. If you turned it off, you, me, your dog, and the planet would fly apart at the speed of light. So how do you find an invisible, seemingly undetectable force of nature? All the forces have related particles that we can see, given enough energy. With the right tool, we can create those force particles. Although, as it turns out, it's taken nearly 50 years to develop a tool that may spot the Higgs. This is CERN's Large Hadron Collider. At full power, it can channel 7 trillion electron volts, making it by far the highest energy particle accelerator ever made. The higher energy levels of the LHC produce bigger collisions that spurt out more massive particles. This raises the odds that out of the millions of collisions produced each second, the LHC will find things humans have never seen before. Things like the Higgs. But the LHC will do much more than find a tiny particle, because what they've really built at CERN is a Big Bang machine. While trying to solve the mystery of matter, physicists realize that they're on the trail of a much bigger mystery, perhaps the ultimate mystery. What happened in the first moments of creation? Right now, thousands of science detectives hunt the Higgs boson, the elusive particle that gives everything mass, the thing that may keep matter glued together. The mystery they are trying to solve is much, much bigger than anyone first imagined. To solve it, they have to go back to the beginning and recreate the first moments of the universe.
In the first moments, just after the Big Bang happened, it was incredibly hot. Billions of degrees. And heat is energy, and that energy congealed into forms of matter, many of which we have already discovered, many of which we only believe exist because of our equations. Most of these things only lived for a trillionth of a second themselves. You know, they were made, they died away, and left children, grandchildren, and so forth. You know. This cascading down from these ephemeral particles into the stable stuff took place very quickly. The stable stuff then ends up congealing to make the stuff that you and I and everybody is made of today. So what we're doing is recreating in the lab the first moments of the universe, and then by surrounding the site of the collisions with these special cameras, detectors, we can record what happened. And so we are simulating just after the Big Bang, making mini-bangs, if you like, in the lab. And from what we find there, we begin to get a sense of how matter, the stuff that we ultimately, 15 billion years later, are made of, first came to be.
John Butterworth is a physicist at the University College of London. Adam Davison is a postdoctoral student. They're two of the 6,000 scientists conducting experiments back at CERN, the European Organization for Nuclear Research.
CERN itself is not terribly pretty.
It looks like someone dropped a load of rusty bricks on the ground.
I get the impression that there was never much of an architectural plan for CERN.
Until you go underground, of course, and then it's like something out of a James Bond villain set. It's fantastic.
This, as a piece of engineering, is a miracle. It is the pyramids of our time.
The heart of CERN is the Large Hadron Collider, a $10 billion, 17-mile-long particle accelerator. It is quite possibly the most sophisticated scientific instrument ever built. The LHC creates the primordial explosions. Then, 4 enormous detectors along the accelerator ring take pictures of the collisions. The 2 largest detectors are called ATLAS and CMS. MIT's Steve Nahn leads a team that helped design and now runs the CMS detector.
We build our detectors to take pictures of the events which happen once every 25 nanoseconds. That's 40 million times a second. We have an interaction that we want to take a picture of. And our detector is made out of several different cameras. You could think of it as having like an X-ray camera and an infrared camera and an ultraviolet camera and a regular photo camera, all at the same time taking pictures of different aspects of the event. So with this terabytes and terabytes of data on disk, we have to write algorithms which sift through and find that event, that 1 in 10 million, 1 in 100 million, 1 in a billion event that you're looking for.
On the other side of the LHC, Butterworth and Davison have developed a way to comb through the enormous amount of data generated by CMS's arch-rival, the ATLAS detector. The 2 men are trying to create maps of what they think the subatomic universe looked like just seconds after its creation, then matching their imaginary maps up to reality. Somewhere in there, they hope they'll find the Higgs.
It's kind of like a border around an unknown country. And we know that it's there. We've had experiments that have gone to high enough energy to tell us there is a border and there is a land beyond it, but we've not had really much of a glimpse of the land. So the LHC really is going to let us over that border and let us have a look at this land and survey it and see. And this is why people, when people ask, what we're going to find when you're going to get your Nobel Prize, we just don't know it. We know that if the Higgs exists, it will be in that country somewhere, and our kit is good enough to find it. It may take a few years, but we'll find it.
Meanwhile, back in America, Fermilab hasn't given up. It's a race against the clock to find the Higgs before CERN's LHC powers up.
Of course, we're here in Chicago, and we'd love to have that machine in Chicago. So we look at the success of our European colleagues with mixed feelings. It's a little bit like watching your mother-in-law drive off a cliff in your BMW.
September 2008. The physics world holds its collective breath as the LHC powers up for the first time. The first low-powered beams shoot through the 17-mile ring, and all is well. They're ready to tear the veil off the universe and try to catch sight of the Higgs. Now they raise the power. 1 more notch on the way up to 7 trillion volts. And then the LHC explodes. September 2008. Explosions rip through the 17-mile-long tunnel housing the Large Hadron Collider, Europe's Big Bang machine. An enormous blast destroys hundreds of the superconducting magnets that shoot protons through the accelerator.
It's pretty dramatic.
Yeah, absolutely.
It took a year to fix.
It must have been quite an electrical arc to melt through the...
Imagine the face of the guy who opened the door to the tunnel. I just don't really know.
Yeah, I can imagine waiting to get in there, right? They must have been really, really nervous to see what had happened.
It was desperately disappointing for everyone involved.
As CERN rebuilds its broken magnets, Fermilab's Tevatron steps up the pace. But they don't see the Higgs. This means that the Higgs particle, the force carrier that allows matter to clump together, has a high mass. And the higher the mass, the more outside energy it takes to crack it open. At this point, Fermilab just can't generate enough energy. December 2009. CERN's LHC restarts. Within weeks, it powers up well past Fermilab's capacity. Eventually, it will be 7 times more powerful. With both machines running, the Higgs particle could be found in the next few years. Unless everyone's secret fear comes true. What if it's not there at all? What if the standard model is wrong and the Higgs doesn't exist?
If it turns out that the experimental evidence is strongly that there is no such thing, then I'm simply baffled, because it means that a great deal of physics, and which I think I now understand, I would no longer understand.
If the Higgs theory is wrong, of course, many theoretical physicists will jump out of second-floor windows. That's about as high as they go.
Nature knows how it works. Soon we will know how it works. We have our ideas on how it works, which may be proved correct, they may be proved wrong. Whichever it is, we will learn. If you're asking me to place my bets, I think that something like the Higgs boson is out there waiting to be discovered.
What would be more exciting is, in fact, we find things that we don't understand. So we understand that the Higgs is going to be there, and so we find it, so hooray, hooray, now what do we do? But if you find something you don't understand, well, now people have a job. My job every day is to go to work and understand things that I don't understand. If I have more stuff to not understand as job security.
So, what are we really made of? Dig deep inside the atom and you'll find tiny particles held together by invisible forces in a sea of empty space. Dig even further, and we discover that everything is made up of tiny packets of energy born in cosmic furnaces. It's energy that cools down, gets dragged through a mysterious force named the Higgs, and clumps together, forming all the things we call matter. It has an evil twin called antimatter. But most of that has long since disappeared. As we get closer to recreating the heat of the Big Bang in our accelerators, we get closer to understanding how and why all this happened. Perhaps someday, not long from now, we'll finally solve the last remaining riddles of matter and fully comprehend the inner workings of creation.